this video explain example to determine deflection in the beam. So let's put some notes here. Determining the deflection, let's say at the free end of a cantilever beam under a point load. All right, now let's draw a beam. So the beam is a cantilever which has a point load of P and it has a length L, right? Okay, now in this case we need to use principle of work and energy, and that is based on external energy equal to internal energy, or external work done equal to strain energy. Now we can first calculate the internal energy stored due to this load P. Now to do this one, we can have a cut in the beam at a distance of x. So where we have make the cut at distance x, we have a axial load, we have shear, let's say we have in this direction we have shear, and we have bending moment. Now we are interested in finding this bending moment. So let's say anti-clockwise is positive, so this is clockwise moment, so it's minus m. This will also clockwise moment, so minus px equal to 0. Please note we are taking the moment at this point. So minus m is equal to positive px, so m equal to minus px. That is the equations. Now to calculate the internal energy ui, we have an equations for the moment for the beam m square over 2 ei dx. Now in this case we can substitute the value of minus px square over 2 ei and dx, right? So 0 to L we have p square x square on 2 ei dx. So p square is become minus p square become p square x square 2 ei dx, and we take the common constant out, and we can have 0 to L x square dx. In this case we can have p square on 2 ei, integration of x square becomes x cube on 3, 0 to L. We can substitute the x values L and 0. That will simplify p square on 2 ei L cubed on 3 minus 0. That will give us p square on 2 ei L cubed on 3, and that will have a p square L cubed on 6 ei. So that is the internal energy due to the load P in the beam. Now we have equations to find the deflections. We need to find this deflection delta under this load P and at length L. Now to calculate that one, we need to calculate the external work done. External work done would be 1 P delta. How we know this one? Because as you know, because of this P, when you have a load P 0, you have, let's say this is 0. When you have load P is 0, you have deflection 0. So therefore you have 0. As your load is increasing, your deflection is also increasing. So that's a linear relationship. Now in this case we can have a external work done, which is the area of the triangle, and area of the triangle is 1/2 base times height. Now this is, let's say, base, and that is height. Now half base, let's say this is the height of this one, which is P, and the base is delta, so delta P. So therefore we have 1/2 P delta. Now to calculate deflections, external work done equal to internal energy. Now external work done is 1/2 P delta, 1/2 P delta. Internal work done is, internal energy is p square L cubed 6 ei, p square L cubed over 6 ei. Now we can cancel this one first, 3. So we have p delta p square L cubed on ei, and then we can cancel this p and this square. So we have finally delta equal to L cubed on EI, and that is the remaining P. So that is the deflections of the beam under, let's say for example, if I have load P, and if these deflections here, that would be delta equal to PL cubed on EI, and this is, let's say, length L. So that's the answer using the principle and work energy. Thank you.